came up with the nemesis theory, the issue was, well, wait a minute, how come nobody found it? And that was pretty obvious. It has to be hard to find.
By definition, a red dwarf barely glows at all.
It would be the closest star to our sun, and we wouldn't even know it. Now, why is that? The way we discover nearby stars is either because they're very bright, and a red dwarf star is not very bright, or because the sun is moving past it. This star is moving with us. Yes, it's orbiting us, but that orbit is very slow, 26 million years. So it would be moving with us. It would just be at a fixed position in the sky and wouldn't move.
In other words, when viewed from Earth, most nearby objects are shifting over time. But Nemesis is sitting still. So, as the search for Nemesis enters high gear, one key question is where to look. Luckily, scientists understand how binary stars orbit each other, and they can apply this knowledge to the search for Nemesis. If both the Sun and Nemesis were of equal mass, they would orbit each other in a vast but equal circle, and the search for Nemesis would be relatively easy. But binary stars are rarely equally sized.
10 or 20% of binary stars have two components where the stars are really on an equal footing. And then there are also a large number of stars where one star is considerably more massive than the other.
When binary stars are of different sizes, the smaller star, in this case Nemesis, swings in a wide orbit around its larger companion, in this case the Sun, which barely seems to orbit at all. Why does the smaller one move in a much wider circle? The answer has to do with a concept called the center of mass. A pair of gymnasts on a balance beam can help us visualize how it works.
Stars in a binary pair orbit around their common center of mass. If two stars are about the same mass, they orbit around an invisible spot in the middle, right in between the two of them, just like Tammy and Carly are balanced on the seesaw. Wow, are you guys balanced?
But unlike these gymnasts, Nemesis and the Sun are not equal. Astronomer Richard Muller estimates that the Sun has 10 times more mass than its undiscovered twin. And when one binary star is larger than its sibling, the center of mass between them shifts closer to the larger star.
So Tammy's going to help illustrate that. Tammy, how much do you weigh?
About 130.
About 130. And we have weights at this end that are about 35 pounds. So you're just a little bit less than 4 times that weight. So climb on up. Let's see where you have to be to balance the balance beam.
Since Tammy weighs about 4 times as much as the metal weights, she must move far closer to the center of mass to maintain balance. If Tammy and the weights represented binary stars, the weights would orbit far out in the distance, while Tammy would barely move. In fact, both would be orbiting each other.
It's kind of a misconception to think that the more massive star doesn't move and the less massive star just goes around it. In fact, they're still both orbiting the common center of mass. The more massive star moves less, and the less massive star moves more.
This insight is key to calculating where Nemesis might lie in relation to the Sun.
We know it's a 26 million year period. That tells us how far out it is. It has a radius of about a little over light year. So we know the orbital size.
Now that scientists know roughly where to look, the search for Nemesis is in full swing. And so far, that search has led to an astounding new theory. Not only might the Sun have an undiscovered twin, the solar system may be harboring a massive undiscovered planet. In the hunt for an evil twin to our sun that shakes comets loose and rains death across the Earth, all of the pieces are in place, except one.
The nemesis theory really needs the smoking gun of actually finding direct evidence for the object itself in order for the whole thing to hold together.
Now, why haven't we found it yet? Actually, there are quite a few astronomers who don't pay very much attention to this and simply assume that if it existed, it would have been found by now. We believe this thing can be found within the next few years. What it takes is a survey of dim stars.
Enter WISE, the Orbiting Wide Field Infrared Survey Explorer. A powerful new tool that just might crack the nemesis mystery.
The reason that WISE is going to be so good is because it operates in the infrared. It sees heat, basically.
By measuring heat instead of light, infrared scanners can make warm but dark objects easy to spot.
The nice thing about looking in the infrared at the heat of it is you don't care how far away you are from the sun.
Jupiter provides an example. The temperature on the surface of Jupiter measures 230 degrees below 0 Fahrenheit. But that's blazing hot when contrasted with the 450 degree below zero temperature of space. So even in the absence of sunlight, a distant Jupiter-like planet would glow brightly in the infrared. By visiting a motor speedway, we can see how the WISE survey might help find nemesis by exploiting the infrared contrast between objects of different temperatures. Here, the roar of the engine only tells half the story.
I came out here today to the Drive Tech Racing School to be in a race car that would go zooming around this track a bunch of times. And the idea was to film the car with an infrared camera and show us things that are hot, hotter than the outside surroundings, and glowing at infrared wavelengths. So hey, Ted.
How you doing?
Good to meet you.
Likewise.
Yeah, you're the driver?
Sir.
Now, how fast are we going to be going?
Approximately 170 miles an hour.
Now, that's about 3 times normal highway driving speed,
Yes,
so
sir.
whoa, things are really going to heat up.
Oh, yeah.
All right, let's go then. Blair Dupree of Drive Tech helped me get into the car.
Protection. This is a nice thick helmet, huh?
And it's not so easy because there's no doors, okay? You have to kind of climb in through a window.
Bring your left foot up in there.
Okay.
Bring your right foot on up.
I feel like I'm breaking into a car. And then kind of slither your way in. Being in that race car was really exciting. When I was going around the turns, I could really feel the G-forces.
Ted, give you a good ride, didn't
Yeah, well, I'm glad Ted was the driver. I couldn't do this, you know? I was scared out of my seat and I wasn't even the driver, okay?
With the car nicely warmed, a FLIR infrared camera, set up by thermal imaging expert Ross Overstreet, sees everything literally in a new light.
Hello, Allie. Hey, Ross. How are you doing?
Doing good. How are you doing?
Good, good. Let's look at these infrared images.
Right now we're pointed at the back of the car. The best way to think about it is it's more of a measurement device than a camera. It's like having a million different thermometers spread across the image. We're actually getting temperature measurements on each of those pixels. Things that are supposed to be hot look like they're glowing, they're red and orange and white. And things that are cold are colored blue and black, and colors you associate with cool objects.
Right.
And you'll notice there's several different hot areas of the vehicle.
Now, I see some variations across the tires.
Yeah, and you'll notice that the one tire is a little bit warmer than the other.
The right-hand tire was indeed hotter than the left-hand tire because there was more pressure on it during the turns. So how hot is that hotter tire there?
We made a measurement earlier of about 190 degrees Fahrenheit, almost the temperature of boiling water on the tires.
When we just look by eye, we can't tell whether something is hotter than something else, but here you can tell, and that's really cool.
Right, and this camera would work just as well if it was pitch black or in the middle of the day. It doesn't care about solar light at all.
The infrared camera sees the racetrack the way the WISE survey scans the dark and faraway realms of our solar system. If Nemesis is out there, infrared should reveal it.
The hot spots of the race car are sort of like warm, glowing objects out in the cold depths of space far from the sun. This is a whole new way of discovering objects. Objects too faint to be seen through a normal optical telescope, but bright enough to be detected in the infrared.
The WISE telescope completed its sky survey in early 2011. But in the search for Nemesis, the results are still inconclusive.
The WISE survey is going to take a long time to analyze, simply because there's a huge amount of data that had been gathered by this craft.
About half of the Nemesis candidates have not yet been studied, but in the next few years, we expect the theory will be either proven right or wrong. Until that time, it is and should be controversial.
That something so relatively near to Earth can be so obscure is what Frank Jankowski of Mobile, Alabama, wants to ask the universe. Why can scientists observe objects in space that are millions of light years away, yet have difficulty spotting objects at the edge of our own solar system?
That's an interesting question, Frank. The objects that are millions of light years away that astronomers can see are powerful and luminous. They produce a lot of energy on their own, like an exploding star. But an object near the edge of our solar system might be small, and it reflects only a little bit of sunlight, so we can't see it at visible wavelengths.
But as scientists analyze the data for signs of Nemesis, they have made a disturbing discovery. Although calculations indicate that Nemesis isn't due back for millions of years, something appears to be shaking up the comets in the Oort cloud right now. Could Nemesis already be upon us? Since the birth of the Nemesis hypothesis, astronomers have been on the lookout for a faint red star that periodically disturbs the gravitation of the Oort cloud comets. This sends them on a catastrophic rendezvous with the inner solar system, including Earth, every 26 million years. But as scientists study the Oort cloud, they have uncovered unsettling evidence that something is disturbing comet orbits right now. Has Nemesis already returned?
If the sun was all by itself and there was no Nemesis, then the comets in the Oort cloud would all have very predictable and regular orbits. They would be very regular in their arrival times and departure times.
Without gravitational interference from anything other than the sun, Oort cloud comets, like juggled objects, could spread out evenly across the sky. However, that's not what some scientists report.
When we look out into the sky and look at where the comets are coming from, their directions tend to concentrate in a certain region of the sky. And one possible explanation for that is that that skew is being directed by the gravitational perturbations from an unseen object that is out there.
Based on these observations, scientists infer that a huge object is disturbing the Oort cloud.